Hello and welcome to the first topic in this new module on machine learning. And now we'll start with this topic, which is Introduction to Machine Learning. So the objectives for this topic is that after the end of this topic, you should be able to define machine learning, distinguish between suitable and unsuitable problems for machine learning. So not every problem is suitable for machine learning. You should be able to tell the difference. Classify machine learning problems into supervised or unsupervised problems. Okay. And then classify supervised machine learning problems into classification, regression, and others. Then you should be able to write the difference between a metric and a loss, and then parameter and a hyperparameter. You should be able to draw a picture that identifies underfitting and overfitting, and write steps for hyperparameter tuning. Okay. So I hope you will be able to accomplish all this by the end of this lecture. And we will have a small demo. And after the demo, we will also release the assignment. So all put together, you should be able to have these concepts very clearly. Okay. So I hope everyone can hear me. All right. Looks like everyone can hear me.
Yes, sir.
All right. So I'll request Sudhakar and Rishabh to relay any questions. Pause me when questions are piling up. Okay. So what is machine learning? Uh, can you please mute yourself? Who's there? I hear someone. All right. So what is machine learning? It's the practice of developing algorithms that use data to discover an algorithm. So this sounds like a tautology of sorts, or a model. All right. So what that means is that what is an algorithm? So the traditional sense of an algorithm is a sequence of steps to which you give an input and what you get is an output. Okay. So let's take the example of bubble sort, right? So you give it an unsorted array, and then you have a sequence of steps that finds the smallest element, puts it on top, finds the next smallest element in the rest of the array, puts it at the second position, and so forth. And you get the sorted array, right? So that's a sequence of steps, so that there's an algorithm to do that. And then you can have more efficient algorithms such as quick sort and so forth. Similarly, you can think of a decision tree as an algorithm. So what I mean by that is, let me give you an example. So let's say I want to make a decision. So I have some sort of a flow chart for a decision, right? So let's say I want to decide whether I want to go outside for ice cream or not. So first question would be, do I have sore throat? Okay. So if I have sore throat, then I should go no, right? Don't have ice cream. So this is, yes, I have a sore throat. If I don't have a sore throat, then I will say, is it hot, right? Is it hot outside? Okay. And then based on that, yes, and then no. If this is no, then I shouldn't have ice cream. Okay, no ice cream. And if I say yes, then I should ask, did I eat ice cream yesterday? If I eat ice cream every day, I'll get fat. So those kind of things. So now this is an algorithm to make a decision about whether I should have ice cream or not. So in the end, I will get a binary decision: yes, ice cream, or no ice cream, right? So this is an algorithm. The rules of this algorithm, the steps of this algorithm are well known. Whereas in machine learning, the idea is that you know the desired output and you know the inputs. Now figure out an algorithm that will which will take the input and give you the desired output or something close to that. Okay, so that it's an algorithm to discover an algorithm. So what are some good examples and bad examples of machine learning problems? So not every problem is suited for machine learning. Okay, so let's start with the good problems. So whenever you have lots of data and the model is not known, so the model from from input to output is not known, but you have lots of data, possibly paired data of input and desired output, target output. Okay, so that's a supervised problem. So I'm jumping ahead a bit, but let's say you know a lot of these pairs, then what algorithm will take you from the input to output? Okay, that is a good machine learning problem. Now, a bad example of a problem that is not suited for machine learning would be when the prediction model is well known. So let's take an example. So looking at positions of the moon, can I predict whether on a certain day I will have a full moon or a new moon or a crescent moon or whatever that is, right? Or can I predict the time of moonrise, assuming there are no clouds? Can I predict the time of moonset or sunrise and sunset? For this, the model is very well known, right? The moon goes into a certain elliptical trajectory, and its reflectance is based on Earth's trajectory with respect to the sun, which is also very well known. Okay, so if the model is very well known, there is no point actually using a machine learning model for this. You might as well write a simple equation that will give you much better predictions than most machine learning models. Or you have too little data. If you have too little data, and then you may not be able to train machine learning models to do anything about it. So for example, I'm talking about one stray dog that has come into near my house, and this is like the third day only that I'm seeing it. My question is, can I predict whether it will chase my car or not? Because I've seen it only for 3 times or 4 times or 5 times, it's very hard to predict whether, at which time of the day, in which mood does this dog chase cars, right? But if I've observed, let's say, other dogs, and then based on that, I want to make a generalization, or if I observe this dog for a long time and now I want to predict its behavior, that might be a good machine learning problem. So if you have too little data, you can always question, can I get some other data to make it more data? So for example, can I get data about other dogs to make a prediction about this dog? Right. So question yourself, if you think you have too little data, maybe you can get data from somewhere else. And there are advanced machine learning problems, paradigms that help you make use of other data that may not be exactly relevant to your data. So things like transfer learning and so forth. But if the model is well known, there's no point using machine learning. So I hope this difference is clear. Yes. All right. So what is learning? Learning is improving task performance based on experience. So there are a couple of things here in this sentence that are packed. Okay. One is task, the other is performance, the third one is experience. So let's say we want to learn to ride a bicycle, right? So the way we learn how to ride a bicycle is we get on the bicycle, we try to pedal, and we twist the handle, we turn the handle, and we figure out under what conditions, if I turn it this way, I'm going to fall. Under what condition, if I turn it the other way, am I more likely to retain my balance, right? So your performance is balancing while moving, right? That is your goal. Your goal is that your bicycle shouldn't like fall down. Okay? And your task is basically learning to ride the bicycle, and the experience is trying to do it in many situations and trying to experiment with the handlebar and the pedals. Those are that's the experience that you want to do, that you want to use. So you need many examples, many hours of riding to get good at riding a bicycle. Okay? So it's a learning process that's happening in our brain. Okay? So whenever we have a machine learning problem, the way we will frame the problem is we will identify the inputs. Okay. So here in the bicycle example, what are the inputs? Inputs are your bicycle velocity and your the existing tilt of the bicycle, and let's say the twist of the handlebar. Okay. So these are your inputs, and then identify desired outputs. Your desired outputs is that the balance of the bike should be near vertical, and then map the problem to some broad machine learning paradigm, whether it is a supervised learning, semi-supervised learning, reinforcement learning, unsupervised learning, etc. and then based on this mapping, you identify the performance criteria. Okay, so I'll pause to take any questions now. Yes, so I mentioned velocity as an input, Aryan. Yes, it will be an input. Velocity can also be an output, but that depends on how you look at it. So if you are only learning how to twist the handlebar, then it can be an input. So it's not entirely clear how you will uh, take care of both. So, question from YouTube: if prediction model is well known, but the computing output is from input is expensive, then it can be a possible machine learning problem to map input to output. Yes, very good point. So that's a more advanced topic. So many times, so in physics, for example, so let's say you want to model an inversion problem, right? So an example of that would be that you have a certain shape in the middle of the room, and you have some sources of electromagnetic waves, and they go through the shape, and then you have some sensors that sense it. So based on the sensing of these electromagnetic waves, can you back compute the shape of the object that is in the middle of the room? And it is possible to do it using very expensive, computationally expensive simulations. So you generate a lot of synthetic shapes, assume their interaction properties with electromagnetic waves, and based on that, uh, you can actually or even for one shape, if you assume some shape, you can or you can back calculate the shape that will give you that sensing pattern. But that's an expensive process. So if you train a machine learning model that takes many such examples, then possibly it can be much faster. So even when the model is well known but it is computationally expensive, then it's machine learning can be a good problem, good solution to that problem. Okay, so Jay,
Sir, can you explain the third point, map problem to broad machine learning paradigms?
can I explain it again? Yes. So what that means is that if you, when you look at the outputs, right? So if you have, let's say, one output for every input, then it's a supervised problem. If you have one output after every few sequence of inputs, then it is a reinforcement learning problem. If you have one output for a group of inputs, then it's a weakly supervised problem. So basically, which type of machine learning problem it is, that is what I mean by that. All right. And whether you have labeled outputs or not. So those kind of things. Right. So some examples of machine learning that is all around us is, for example, when you type in a swipe keyboard on your phone, you add new words if you're using uh, Roman letters, which is English letters, to write Hindi words or Telugu words or something, then it starts to pick up your swipe patterns for those words, and it will start to predict that better. Same with you will see in Gmail and some other Google services that when you type something, it will try to finish your sentence before you finish the sentence. So it has learned the pattern of the queries or the sentences that are added that are entered into that service, and based on that, it is predicted. Another example would be spam, right? So filtering spam from email. So certain email services are very good at it. Squirrel Mail or Webmail are not very good at it, but let's say Gmail is pretty good at it. Yahoo Mail, Outlook, those must be very good at it. So how they do that is they have looked at a lot of emails and your labeling and several other users labeling of what is spam and what is not spam. So if you were to just do it based on just keywords, some rule-based algorithm, like a decision tree of having ice cream that I mentioned. So if you try to make a decision tree of what is spam and what is not spam, you might want to look at keywords such as you are a winner, something like that, right? So if that is most likely a spam mail, but it pretty soon becomes much more complicated than that. And some genuine emails can look like spam, some, and spammers are getting smarter and they are trying to make emails more like personal mails and so forth. So you'll quickly run into a problem where you will not be able to write a rule-based algorithm. So it's better to let a lot of people label what is spam, what is not spam, and have a machine learning algorithm figure out the rules based on that. Sir, what do you mean by well-known problem? And can you explain with an example? So well-known problem means the physics is well-known. Like for example, uh, predicting sunrise and sunset. The physics is very well-known for that. So it is you don't really need to use machine learning for that. You based on the equation of spin of the Earth and the revolution of the Earth, you can predict sunrise and sunset, and based on your longitude and latitude, right? So that's an example for which you don't need machine learning. Um, and then other examples of machine learning problems could be, for example, if you take more fancy examples, self-driving cars, which has not just one but several machine learning models working in tandem. Some are processing the inputs from the camera, some are processing the inputs from the lidar, some are monitoring the traffic situation on Google Maps, and based on that, it is trying to do the route mapping and so forth. Okay. So there's several machine learning algorithms that might be working in tandem. Then things like face recognition that you see on Facebook, right? So as soon as you upload your picture, it starts suggesting you who to tag, including yourself. And it's very difficult to write rules for what is your face based on the pixel values. So if your image size is 200 by 200 pixels, so you now have 40,000 pixels. So using 40,000 numbers, it's very difficult to write an algorithm. So it's better to do it using machine learning. Okay. So now let's look at the relation of machine learning to other fields. Typically, we tend to think of machine learning as a subset of artificial intelligence. So artificial intelligence just means that you have machines that have behavior that you would consider to be intelligent. And that could just be rule based. You can have a very complicated rule based system with which was earlier called expert systems, with which can give you intelligent behavior. Or you can have a search strategy like A star, which is also considered artificial intelligence. But a subset of that which learns from examples based on statistics and advanced form of statistics, or statistics of many dependent variables, that is machine learning, right? And neural networks is a type of machine learning framework. There are several other machine learning frameworks, support vector machines, SVMs, random forest, they are all machine learning frameworks. And then neural network is just one type of it. And when these neural networks become very big, usually very deep, then we call it deep learning. So this is how I tend to think of the relation of machine learning with all the other branches. Let's look at a few questions. Uh, so what do you mean by well-known? Also, I took that already. Is riding a bicycle an example of supervised learning problem or a reinforcement learning problem? So riding a bicycle is more like a reinforcement learning problem because you don't know when you are going to fall. Your initial few milliseconds of handle twisting doesn't tell you whether you are falling or not. Is there a boundary between AI and ML? So if you're not using examples to refine your rules, then it is not ML. Then it is not machine learning. Then it could be AI, right? If it is still intelligent. Okay. All right. Yeah. Searching, for example. Yeah. Sujay, you had a question?
Sir, I used to think that deep learning and neural networks were the same. I thought that neural network was deep learning. So what is the difference between neural network and deep learning?
So neural networks also include shallow learning, shallow neural networks. So there are deep neural networks and there are shallow neural networks. So whatever came, let's say before 98, those are most of them were shallow neural networks. And
Okay.
after 98 also, deep neural networks did not pick up until like 2010, 2012.
Yeah,
Until
it
we
has
had
become
yeah,
famous more recently.
yes, yes. So in 2012, 2010, 2012, when people started using GPUs and in general computing power became more, then the neural networks became deeper. One of the key developments was the invention of the convolutional layers, which actually happened in 98, but didn't get popular until the early 2000s.
Sir, to make my question clear, can you tell me what are the different deep learning architecture and the neural network architecture, so I will get a clearer picture.
So if you have a neural network where you have one input layer, one hidden layer, and one output layer, then it is not a deep network. Okay. If you have a
Oh,
neural network which has three convolutional layers, two fully connected layers, so total of let's say 5 layers, and then an output layer, then you can consider it a deep learning problem, deep learning
so
neural network.
one question: do you consider LSTM as a deep neural network? Because
It
it is recurrently calling itself, but the layers are not that much.
Yes, so the LSTM is now considered deep learning. It's because I think it is recurrently, yes, it is calling itself, but I think the idea is that these are still very large neural networks, and the gradient at least is going many steps horizontally, if not vertically.
So basically, to solve these,
Okay.
you might have to unroll the looping, which
Yeah,
takes it to deeper levels, and hence it falls within the category of deep learning.
yeah, and then now the state of the art transformer networks, they have like 6 layers, 7 layers sometimes. So one question: how do you know if a system is intelligent? There is no strict definition of it. If it doesn't look dumb, then it is intelligent. I mean, if it is doing some sort of adaptation to input, so searching sometimes is also considered. Some sort of searches are also considered intelligent behavior. Okay.
I think the great idea here would be to look into Turing test. So just
Yeah.
Google that, and probably that would give you early ideas of how intelligence was defined. So look for Turing test.
So another picture to tell you the difference. Thanks, Jyoti. Another picture that tells you the relation of machine learning to other fields. So machine learning is supported by linear algebra, probability and statistics, optimization, and data science. And hopefully they are not taking machine learning to its funeral, but I thought it might help explain the 4 pillars of machine learning. Okay. So types of machine learning problems in a nutshell. Oh, looks like some chat questions have piled up. So most of these are explanations. Great. Okay. So types of machine learning problems. Supervised learning. So this is the workhorse of machine learning. Basically, what and yeah, most of the time when we talk about machine learning, we are talking about supervised machine learning. Although now the frontiers have shifted towards self-supervised, semi-supervised, reinforcement learning, etc. So what supervised machine learning means is that the examples that we are talking about from which you explore and get the rules that give you good performance, those are based on labeled data. So what labeled data means that for every input, the output in the training phase is known. So for example, if I want to do face recognition, then I have let's say 100,000 faces, and for each of these 100,000, the label for which person it is. So let's say there are 1,000 people are there in this 100,000 mix. So which of those 1,000 persons is represented by this one image, that is known, whether it is Amit or Ashish or Jyoti or Sujay or whoever it is. So that label is given, right? So when this label is discrete, then it is a classification problem. So for example, telling what is the species of this flower based on characteristics of the flower, that is a classification problem. Same with the face recognition. But if the labels or the target variable is continuous, then it is a regression problem. Example would be, let's say you are given a picture, and from the picture, can you guess the height of the person? So person's full length picture is given, and can you guess the height of the person? So now height is a continuous variable. But now let's say you were given 10,000 such examples of pictures with heights given in centimeters. So that would become a regression problem. Who is unmuted? Yash, please mute yourself. Okay. Uh, And then there are other types of supervised learning problems. For example, ranking. So given these 1,000 photographs, can you rank them in aesthetic order? Okay. So aesthetic order. So what is aesthetic order? I mean, it's there is no objective measure for it, but let's say we get 100 people to vote in them, and then we look at the average votes, and can we predict how people would have voted for these? So the order in which they have voted instead of the actual vote count. So if it is actual vote count, then it is regression. If it is the order of the ranking of the vote count, then it is a ranking problem. Okay. All right. Let's look at some questions. Does game playing come under AI? Yes, if the computer, you are teaching the computer to play the game, that's an intelligent behavior you would like it to have. So if it is earlier, for example, chess programs were all rule based, so then it was AI but not machine learning. Now a lot of it is being done using machine learning. Uh, so it's specifically reinforcement learning. Okay. Uh, does Google's PageRank come under ML? So that's I don't think you would call it a because the algorithm is fixed. The PageRank algorithm is fixed, so I don't think it is ML. You can call it AI, but you probably cannot call it ML. But I think they have moved far away from the original PageRank algorithm, and probably now they are based on ML. So what makes it an ML algorithm now versus back then when it was PageRank? In PageRank, the algorithm was fixed. So how many other pages linked to this page and those kind of things were taken into consideration. Probably now what is taken into consideration is also what is in the news and what is in the news in your territory, in your, let's say in India or in Maharashtra. So based on that, the search results might be different, right? So it's now even more intelligent than PageRank, and that is probably based on machine learning. So what is the label for this machine learning problem for the PageRank algorithm? That is basically do you really find the search results in the top 2 or 3? How will you do that? Based on, they will monitor your clicks. If you are scrolling down to click, then their algorithm gets a feedback. I mean, their data center gets a feedback that your algorithm is not good enough. So after 2-3 days of collecting that data, you can retrain that algorithm. Okay. All right. And then you have unsupervised learning, where you really don't have any labeled data. So you just have a lot of data. Two classic examples of that are clustering and dimension reduction. So given, let's say your customers, so you have 10,000 customers, can you divide them into 3 groups so that I can target them using different marketing strategies or different customer service strategies, right? I don't know what those are. I can't predict. I don't have a label that this should be gold customer, silver customer, platinum customer. uh, but let me see, based on how much they order from me, how frequently they order, what kind of product mix they order, based on that, are there any natural groups? So that is clustering. Similarly, there's something called dimension reduction. So if you have, let's say, 10,000 genes that represent a patient's cancer, then can I represent it using 5 numbers? Can I reduce these 10,000 numbers into 5 numbers that pretty much describe the entire data? That's dimension reduction. Someone is unmuted. Prasoon, please mute yourself. Okay. Questions. Target labels are given. Okay, yes. Yeah, okay, great. Example of ranking. So ranking, for example, ranking the aesthetic quality of images, ranking survival of patients. So which patient will die first, which has worse cancer than the other, and so forth. So how is PCA different from dimension reduction? PCA is a type of dimension reduction. Okay, it's a linear dimension reduction. There are non-linear ways of dimension reduction as well. Ashish, what's your question?
Sir, my question is in terms of implementation, when we compare classification and ranking, what is the difference? Because like labels are categorical in nature, so when those algorithms must be implementing, right, like they like, do they give importance to ordinal features? I'm not aware about it.
Yeah. So you can form loss functions, such as you can compare You can compare each like pair-wise samples and make sure that the output for the higher ranked one is higher than the output for the lower ranked one, right? So those kind of pair-wise comparisons you can do.
So
So
is
there
there
are
any famous one that you can like kind of name or something which does this? Because like this is like I'm not aware about this.
so look this up, MTLR,
MPLR.
MTLR,
Okay,
the
thank you.
multitask logistic regression.
Thank you, sir.
Okay, Sujay.
Sir, genetic algorithms are also a popular machine learning algorithm paradigm. So, which category do they fall in? Like which type of learning?
So most of the genetic algorithms that I have looked at, they fall under supervised learning. So the fitness, you already know the fitness, right? So you're trying to increase that fitness.
You said most. That means there are that it also falls in other categories also.
I'm not very well versed. So I took genetic algorithms like way back in 2001, I believe. No, 1999, 99 or 2000. So after that, maybe a lot of it has picked up, but I've never found it very appealing. Maybe it is used for some hyperparameter tuning and so forth, but
Any reasons for it being not appealing?
I mean, see, genetic algorithms are good for when your input space, right, is very discrete, and you are labeling, you are coding everything as a binary variable or some sort of a discrete variable. A lot of interesting machine learning is when your input space is continuous and there's some contiguity in the data. If two inputs are closer to each other in some sense, then they must belong together, even whether it is regression or classification. But genetic algorithms are more like, it's the difference between convex optimization and what is it called, integer optimization, or something along those lines, combinatorial optimization. So that's the analogy that I would give. Ram Mohan.
Sir, in the case of clustering, so we are given a bunch of data points and we are trying to form natural clusters in them. So basically, we are trying to find premium, like in some sense, premium gold naturally. Is that what?
Yeah, so let's say, I look at my customers, right? And I look at the margin that I get from them, right? What percent of profit I make from them for every sale. And I look at their sales, right? So there's bunch of them here, there are bunch of them here, there are bunch of them here, and so forth, right? And so this, like, let's say, and let's say some of them are here, right? So this really is a premium customer for me, right? I should do everything to keep them happy. They give me more sales, they also give me more margin, right?
Yes, sir.
And these are the ones that even if they leave me, I don't really care, right? So can I find such natural clusters? That is the question, right?
So
So here it's a simplified cartoon where it looks like there are 4 clusters, but it may not be obvious all the time. So,
yes,
question.
sir. One more thing in this. So let's say we make these clusters.
Yeah.
Uh, how can we see if we did a good? How can we measure if we did a good job or not in this case?
Yeah, so we are jumping ahead now, but basically what you see is that inside a cluster, the distance should be small. The distance between a point inside the cluster and to another point outside the cluster should be large. So if you take the ratio of these two on an average, then that will give you an answer about whether you did a good job or not. Okay. All right. So somewhere between supervised and unsupervised is semi-supervised learning, where you have some labeled examples, some unlabeled examples. Weakly supervised learning, where you have label for a group of examples, but not for individual examples. I'll give you an example of that. So let's say you have a slide, right? So this slide is taken from a tissue from a biopsy, right? So you want to see that so this is a cancer tissue here, right? So we know that this person, given a particular chemotherapy drug, survived or not survived. But so I know from this slide that there is evidence in this cancer tissue that this is worse cancer or not so bad cancer. Okay, but I don't know where it is. So if I look at like small patches of this, right? So I have a lot of patches, and I know that maybe some of them, maybe one of them or two of them is where the worst cancer is, and rest of it is not so bad cancer. But I don't know where that is. So that's a weakly supervised problem, that I have the label for the entire set of patches from this slide, but not for individual patches. Compare that to another slide of a second patient, where this patient actually had pretty good, I mean, not so bad cancer, and with chemotherapy, she was treated. Okay, so here I know that all of them must not be bad type of cancer. They must be like the not so bad type of cancer. But in the other one, I know there is bad cancer somewhere, but I don't know where it is. So that's a weakly supervised problem. Clustering is unsupervised. Anomaly detection is supervised, or mail spam is not, is or not, right? Yeah. So if you want to do anomaly detection, then it's a supervised problem. You can think of it as it's actually a hybrid between the two, right? So if you don't have anomalies labeled for you, then basically you are saying that it's it's a hybrid between supervised and unsupervised, that only normal samples are given, and then you're trying to form a tight boundary around them. Okay. So that is weakly supervised problem. We talked about anomaly detection also, which is not on the slide. And then reinforcement learning, where you take a sequence of steps, such as when you're playing a game, but whether you won or lost is known after a sequence of steps. So the label comes after a sequence of steps. You don't know what happened or which steps that led to that failure or success was responsible for it. Okay. So that's like a bicycle learning. So when did you start taking the wrong turn on your handle that led to your fall? Okay. So the workhorse is the supervised learning problem, where you have target variables. So let's say you have the target variable is a categorical variable. Okay, so then it's a classification problem. So let's say we have three different species of flowers, and several examples of those flowers are given using their sepal length, sepal width, petal length, and petal width. So this is really the UCI, one of the UCI data sets, flowers data set. So here um, the task is that you take these four numbers. So each row is one sample. Okay, each column is a feature, and the last column, or sometimes the first column, depends on how your data is arranged, is going to be the label. So you're using these four columns to predict the last column. Okay, so you have four features or four inputs, and you have to predict the target variable or the label. So that's a classification problem. So here it is categorical. There are three different species in this particular data set. If the target variable was a number and a continuous number, then it would be a regression problem. So one of the easiest ways to do both classification and regression is to do k nearest neighbors. Here you don't have to really do any learning of any sort. So what we are going to say is that let's look at the two classes. Here you have red and green. Okay, and what is x-axis, what is y-axis? The x-axis is feature 1, y-axis is feature 2. Okay, so here, given any point in the space, okay, so when is machine learning useful? It's not useful for the points for which you already know the label, right? If you already knew the label of all the flowers for which you have done the four measurements, then it is not useful at all. That's just a table, lookup table. But given a new flower, given a new flower for which you don't have the exact measurements, but you will measure them when you go to the field, would you be able to predict that flower, right? So it should work in new situations. And the key to working in new situations is to divide the input space or to transform the input space. So basically take these four, so you have a four-dimensional input here. So four features means four-dimensional input. Either, so both transform and divide the input space in such a way that you form regions in that input space where the label is the same. So that regions where there's a contiguity inside the region, that is important, right? So one way to do that in using k nearest neighbors would be that for any new point, so new point would be in the white space, not these reds and greens, because for that those we already know the label. For any new white point, you find k nearest neighbors for which the labels are known. So they are either the red points or the green points, but the nearest 5. And then do a majority vote. Usually it's an odd number so that the majority vote can break the ties. You don't look at 4 nearest neighbors, you would look at 1 or 3 or 5. So based on that, you would decide what should be the label for that particular sample. This is for classification. If you were to be doing regression, then you would take some sort of a uh, weighted target variable for those 5 closest points, that label points that you found. Okay, so there's no learning to be done, and for many situations that could be it could give you decent results. The reason to not that this is not very popular is if you have a lot of points, right? If you have 10,000 training points, 20,000 training points, then finding the nearest neighbors itself becomes a computationally expensive task. And then it doesn't allow you to transform the data space. Okay, so it doesn't take this x1, x2 variable and transform it to some new variables, phi of x1 and phi of x2. The other thing to note here is that the concept of what is near and what is far, that is very important. You have to keep that in mind. If I scale the x dimension and do not scale the y dimension, or let's say x1 dimension I scale and x2 dimension I do not scale, then which is your nearest neighbor, that is going to change. Okay, that can change. So that's why scaling of dimensions is a very important concept in many machine learning algorithms. That's why we do things like data normalization. We'll come to that in a bit. Okay, so k nearest neighbor is not a very good machine learning paradigm. So we use some more advanced paradigms such as support vector machines, random forests, neural networks, etc. So for this, the packages in Python that you will use is scikit-learn. And for more advanced neural networks, you will use TensorFlow and Keras. Okay, so now there's a key concept in machine learning, which is parameters and hyperparameters. Before that, let's pause to take some questions. So what are some questions? Um, Saurabh, what's the question on YouTube? Under what conditions is clustering considered supervised learning? Clustering is not considered supervised learning. If you already knew which clusters to send the training data into, then it becomes a classification problem. So then it becomes, yeah, classification. What would happen if a new flower is completely not known while training? Yes, then you can get bad results. Under what conditions is okay. What is the best way to find out k of the k nearest neighbor? There's something called validation. We'll come to that shortly. Validation is the answer to a lot of things. How would you choose? What is the question? How would you? Hold on, I lost the question. It scrolled up so fast. Uh, how would you choose the axis where to plot the points in k nearest? Where what does the distance between points signify? So distance between points signifies the x1 value and the x2 value for the two features. So for example, in the petal, in the flower problem, we had x1, x2, x3 and x4. Okay, any other questions? How do you say that our clusters are good? Yeah, so clusters are good if within the cluster the distances are relatively small, but outside the cluster, from one cluster to another, the distances are large. That's a intuitive way of thinking about it. Suppose you are working on the data set that has both continuous and categorical variables. Which distance metric can you use in that case? Then you would have to convert your categorical variables into continuous variable using something called one-hot encoding. Ramohan, what's your question?
Sir, you said we cannot transform the input space in this case, k nearest neighbors. Is there
Yes.
a particular reason for it? Because in 11th and 12th, I think in some questions we transformed like normal coordinate space to radial space or something.
Yes, so you can, but you have to know what transformation will work for you, or you can keep trying transformations. Machine learning is about finding those transformations sometimes as a part of the optimization process itself. Okay, so it's not about guessing the transformation.
Sir, there is a question that how do we, in case of clustering, how do
Yes.
we, if we have a new data point, then
Hmm.
how do we identify its cluster?
So let's go back to the clustering example. So let's say these are your clusters. So then k nearest neighbor, the strategy is that basically, sorry, let me change the ink color. The strategy is that you draw boundaries that are equidistant from all the clusters, right? Or equidistant from two different clusters. So if the point falls here, then it belongs to this cluster. If the point falls here, it belongs to this cluster. If it falls here, it belongs to this cluster. Here again, it belongs to this cluster, etc. Just give me a second. Hello, any other questions? Okay, so Abhinandan, what's your question?
Hi, sir. Actually, in k-neighbors method, like
Yeah.
when we define an axis, like we have a two features, like you have showed examples, like we have two features, let's say one in x-axis and another in y-axis.
Yes.
Okay, so in the x-axis, if we select a units, if we like since we are taking a distances, let's say we are taking x1 square plus x2 square. So
Yeah.
putting the different units will also give a different weightage to the features
Exactly.
that that
Yes.
may so how will we
Absolutely.
do? Yes.
Yeah. So the practice is to normalize the features so that their variance is one. So that is one way of
Okay.
doing it, or min max based normalization. So we'll talk about it later.
Okay. Okay.
Okay, so now there's a key concept in machine learning models, which is the difference between parameters and hyperparameters. Okay, so this is something that you should be you should know very well. So what's a parameter? Parameter is something that you will change during the learning process. Okay. During the training process, your parameters will change. So for example, the weights of a regression model, weights of a neural network, the variables that you will use for splitting the decision tree and so forth. Those are all things that will change. Hyperparameter are things, are entities or the variables that you do not change during the training process. Do not change during, more specifically during the optimization process. Okay. So this is your design choice that you keep fixed. So for example, let's say I have a neural network, right? So in neural network, let's say uh, I have some inputs, right? So the four inputs that we had for those flowers. So these are the four inputs. Okay. And then I have three different neurons, and I basically uh, take these inputs, multiply them with some weights, and then I give it to this neuron, and then after that I have four neurons to give you the classes, or the three neurons to give you the classes, right? These classes are the three species of flowers. So again, this is connected here, here, and here, right? So how many neurons did I choose in the middle layer? So see, this one is fixed because I have four inputs. So this is fixed because I have three species. This is also fixed. But in the middle, I can have more or less neurons, and I can also add more layers. So how many neurons I will have in the middle layers, or how many layers will I have, that does not change. Okay, that is fixed once I have chosen it. What changes is what is the weight here, 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 etc. So these weights are the parameters. The number of neurons which does not change during optimization, that is the hyperparameter. Is that clear to everyone? This is a very important concept. Okay, so in k nearest neighbor, I'll not go there. Where basically k is the hyperparameter in that case, but it's a non-parametric technique anyway, so there are no parameters per se there. What else is there? What are those middle layers exactly? We will come to that later. I'll explain that later. I'll give you better examples. Abhinandan? Sujay?
So, sir, you said non-parametric learning. So can
Yeah.
you throw light on it?
Yeah, so once I tell you parametric learning in a bit, then I think it will be more clear.
Okay, sir.
So there are like no weights that you are changing. Your training points are training points. They are not like there is nothing you are optimizing after that in k nearest neighbor. You're optimizing the search process for the nearest neighbors, but you're not optimizing any weights or coefficients. All right. So here's a simplified view of supervised learning, and this should possibly clear any doubts about parameters and hyperparameters. So you have an input, right, which goes into a learning system where you are doing the training. And because it is supervised, you also have a target output. You want this to go inside and give you, and basically you want a function to compute an output y, and you want that y to be as close to t as possible in some sense. Okay, and you don't want to form a lookup table of xt pairs, xi and ti pairs, because that defeats the purpose. You want it to perform well for new x inputs. So you will put it inside a model. How the model is structured is fixed using the hyperparameters. So for example, this model is nothing but an equation. Okay, so this model could be something as simple as uh, uh, what do you call it? A polynomial equation of x. So you have x, and then your f of x could be something like w0 plus w1x plus w2x square dot plus wn x to the power n. Okay, so it's a polynomial in x. So this y is equal to fx is nothing but a polynomial in x. Now your n, what is the degree of this polynomial is a hyperparameter. And what are these weights? These are parameters. So once you have chosen the degree of the polynomial that is fixed, what you are going to do is you are going to run an optimization process, which basically setting some derivative to 0 or trying to get close to a 0 derivative, such that you by changing these weights w0, w1 up to wn. Okay, so that is your model. Your model has parameters and hyperparameters. So hyperparameter is n for the polynomial, and parameters are w0 to wn for this polynomial. Okay, so your output is y is equal to fx. Now, because you have this output y, now you can compare it to the target value, the desired value t. Okay, and you compute some error which we call the loss. Now error can be positive or negative. Usually you want both positive and negative errors to be equally responsible for the bad performance of the model. So you would have a loss function. You would, let's say, do the square of the error or the absolute value of the error, and then you will use that error and feed it into a learning algorithm, which is basically an optimization routine, which will change the parameters. So it will read the entire model, okay, and it will change the parameters. And this loop of training will keep going until you have changed the parameters in such a way that the loss is quite low for a majority of your training samples. Once you are done with that, then your model is ready. Okay. And then once your model is ready, you can deploy it. And once you deploy it, you just give it new input x, and it's a fixed model. The parameters are no longer changing, and you just keep computing y, and you live with the consequences of it. If it does not perform well, then you need to collect more data, more target variables t that are paired with x, and then train it again and maybe make it a new model by changing the hyperparameters also. Let's look at the chat. Speech analysis is an example of semi-supervised learning. Okay. In KNN, the output is a class membership. An object is classified with a plurality of votes. Yes, that's correct. What are those middle layers? We'll talk about that later. Hyperparameters predefined cannot change during the process. Yes, but we tune the hyperparameters in some situations. That's also true. That's more advanced. We'll not get there. Questions from YouTube. Can you please define self-supervised learning? That I have heard somewhere. So self-supervised learning is about using unlabeled data. Note the sound. It's unlabeled data, but you somehow create a supervised learning task from that. So let's give you an example. Let's say you want to learn something about images. Okay, so jumping ahead here again. So let's say you want to learn something about images, right? All you have is are images. You don't know what it is an image of. Okay, so in what you can do is you can create an arbitrary task where I divide it into 4 different sub images and I jumble the order and I create a jigsaw out of it. I put this here, I put this one here, and then I put this one here, etc. So I jumble it. I jumble the 4 pieces, and because I know how I jumbled it, I know how to unjumble it. But a neural network does not know. So I will train a neural network to unjumble it. Because of that, it will start to figure out that these 2 shapes have to be in this order, spatial order, these have to be in this order, this have to be in this order, without knowing what the object is. So it starts to learn something about the object without actually, without giving it any label. So that is self-supervised learning. Same thing you can do in text. So if I have a sentence and it's like a workhorse of natural language processing, I will go to the market. Okay, and I cut this word. Instead I give you a blank here. I can take several examples, several sentences, and train a neural network to predict the missing words. In order to do that, it will start to learn the structure of the language without actually knowing what is this sentence, whether this sentence has a positive emotion. Let's say we are doing sentiment analysis, positive sentiments, negative sentiments. Without knowing whether it's a positive or a negative sentiment sentence, if I just train a neural network by taking free data, which is just sentences, without knowing the label positive or negative, I can train it some sort of a language model by training it to fill out the missing words. Okay. All right. Any questions? I guess chat is going fine. All right. So now let's take a concrete example. Let's take the example of regression. Okay. So in regression, let's say I have an input X. Now I have you'll notice an index here, which is X sub I. Xi means it's the ith X. Now if you look at the example on the right, okay. So here you see blue dots, right? So let's say we have value of houses that we want to predict based on a number of factors, such as one factor is number of rooms in the house. Let's say other could be square footage, another could be number of bathrooms, another could be the location or the pin code in which the house is, and so forth, right? So let's say I don't have a whole lot of information. I have only one information. What is the number of rooms of that house? Okay. And so that is my X variable. So that is my input variable. And what I want to do is I want to predict the value of the house, which is my Y variable. So each dot that you see here in this dot, 7 is the number of rooms and $10,000 is the target variable T. Okay, so the blue dots are X and T. They are not X and Y, they're X and T. Okay, so for each input Xi, I have a Ti that is given to me. So that's the label. It's a regression label. What I want to do is I want to model the relation of blue dots, the X and T relation, using a function fx of theta. So here it should be xi, x sub I here. I want an fx of theta. What is theta? Theta is the parameters that I will change for in the model, which are a and b here. So let's say the simplest model I can come up with is an equation of a line, which is ax plus b. Ax sub I means it is the ith sample, which will give me yi. Now what is this yi? Xi and yi form the black line. The blue dots are xi and ti. The black line is xi and yi. Okay, for any given x, a linear combination will give me that. Now which line best represents the blue dots? The line that best represents the blue dot, for that I need to have a performance metric. Okay, and I want to, so let's say I will call that performance metric a loss function or an error function. I want to reduce that error function. I want to find values of a and b such that I get the smallest value for the error function. Okay, so that is basically what the learning problem is. And what A does is it changes the slope of the line, and B changes the y-intercept of the line. If I increase A, the line will become steeper. If I increase B, the line will shift up. The entire thing, without changing its slope, it will shift up. Okay. So I defined a loss function. So any Ti that is lower than yi is a problem. Any Ti that is above yi is also a problem. So I will take the difference and I will square it, and I will take the sum over all the points, and I will say that let me try to reduce it by finding a good values of a and b. Okay, so that's your learning problem. And from linear algebra, we know that we can do this using a pseudo inverse, which is one way to go about it. What we'll do is we'll do this using an optimization process, because it's for large number of points, it's less expensive, and then you can add more things to the optimization process. So let's move further. So now this particular modeling process need not be as straightforward as this. Maybe you will have more than one variable. Maybe you will not just have number of rooms, which is x1. You will also have other things such as number of bathrooms, average income of the neighborhood, etc., etc. So you have n different inputs. Then it becomes a multivariate regression problem, and now you have to find all the coefficients a1, a2 up to an, and then also the bias b, which is the shifting of the. Now it's not a line anymore. It's shown as a line because I can only show you one x. But let's say there were multiple x's, it will become a hyperplane in n-dimensional space, or in n+1 dimensional space. So now the question is, the hyperparameter here is that, should I just use one power of like x1 to the power 1, x2 to the power 1, x3 to the power 1, or should I start to include polynomial terms or power terms? Should I use xi to the power p? And if I do that, should I also have product terms such as xi to the power p times xj to the power q? So that design choice is your hyperparameter. Okay. Whereas a1, a2, whatever, an, and then for new a's, if you have power terms and product terms, those and the b, those are your parameters. So another key concept in machine learning is regularization. So in the informal definition would be that you don't want your model to be so free that, or so wild that it overfits. Okay, so here's an example that is shown in the bottom. Look at the graph on the right. So let's say you have x, which is time, and y, which is like some value that you want to predict. And the black dots that you see in all three figures are the same. You want to find a good relation between y and x. Okay. So if you give the model too much freedom, it will try to touch every point. It will try to come very close to every point. But obviously, this sort of a zigzag situation that you see here doesn't seem like it looks like it is not taking into account that there could be some noise in the predicted output, in the target output. There could be some noise in the y or t, whatever that vertical axis is. So if there is noise, then it will try to model the noise as well, and because of that it will overfit, in the sense that it will, now look at the last part of it. Now this very high degree polynomial type of behavior, it might actually go very further down just outside this range. So if you get another point which might be like here, it will actually predict it to be here because it is going further down here like this. So between the three, this one is a good balance because the other one is too simplistic. the first one is too simplistic. It is trying to model this U shape with just a line. Okay. And we get roughly a U shape in the middle one. So left one is underfitting, right one is overfitting. The one in the middle is perhaps a good fit. So a regularization tries to bring models from the right hand side to the left hand side. If you over regularize, then you go further left to the underfitting regime. Okay, let's take some chat questions. Why do we take squares and not absolute value? Good question. So we can take absolute values. It works. It also works fine. The idea about taking square values is that we want to bring errors that are much larger closer to zero much faster than the errors that are already close to zero. If you have absolute value, then it treats both errors the same way. Small, yeah. Okay. To make regularization more intuitive, you have to have a model. Okay, so that's an explanation. Our ultimate aim is to find minimum error. So our ultimate aim is to find minimum error on held out data, not on training data. That's a key important difference. So between the three that I showed you, overfitting will always give you low error on training data, but that is not the goal. See how close it is to every point here. That will give you very low error. So if you look at the vertical difference between a dot and the curve, it is very small. But that is not the goal. The goal is that for an unseen point, for a new point, the error should be low. But what is an unseen point, right? So that is what we are building towards. So your regularization tries to bring some the overfitted models towards a good fit models by restricting the model, not letting it too wide. So there are different kinds of regularization. One is called ridge regularization or L2 regularization, where you take the sum of the coefficients, square of the coefficients, and you say that that itself will be a penalty in addition to the square error of y and t. Okay, or you can take the absolute value, that is the lasso regression. So this we'll cover these later. Okay, so when you have the data set, to find out whether you did right amount of regularization or not, whether you did the right, whether you chose the hyperparameters correctly or not. So your regularization penalty itself is a hyperparameter. Let's go back here. So here the alpha. So what is this OLS loss? OLS loss is nothing but this loss, sum of yi minus ti whole square. Okay, maybe divided by n, divided by the number of points, maybe divided by 1 by 2n or something. And then you add another term to that loss, which is alpha times sum of ai square. So these are all the coefficients. So this alpha is something that you can tune. You have to choose it. So that's your hyperparameter, right? So whether you chose the hyperparameter to be correctly or not, for that you have to divide the data set into 3 sets: training, validation, and test. Okay, test data you don't touch until the end. Test data is sacrosanct. You do your parameter tuning on training data, your hyperparameter tuning based on validation data, and then once you are done with everything, then go to the test data. Okay, so what is test data? Test data is you took the input data, you kept some aside to see that I will not use it for training, and will it still perform good on this? Will it overfit on the training data? So for that, I will use it in the end. In between, I have a middle stage test data, which I call validation data, right? So when I chose the hyperparameters, alpha value 1, alpha value 10, alpha value 100, whatever that is. So for each of these, I want to see which one works best. For that, I will use the validation data. I will not use the testing data. Testing data is to be used only once. So your validation data should be representative of the test situation in the deployment. Otherwise, you are fooling yourself. What that means is, if you choose an easy validation data, which doesn't have hard cases, which is very similar to the training data. So let's take a concrete example. Let's say you are training a neural network to identify COVID cases versus non-COVID cases using chest X-ray. Very relevant example of the time. Let's say your training data comes from one particular hospital, Nanavati Hospital. Let's say you split that into training and validation. You do the training, you test it on validation, and now you are happy that it works well. Does that mean that the same model will work in Korea or in Italy or in Spain? It may not be the case. Why? Because most likely the brand of the machine that you use to collect the data, the X-ray machine, was the same single machine in Nanavati Hospital, whereas you are using, let's say, Philips versus GE in another hospital. So will it work on the new machine, or will it work on the different brand machine and so forth, right? So only if your validation data also represents that kind of differences and it still performs well, only then you are assured that it will perform good in a new situation. So generally we split the data into training and testing, or training, validation and testing, which would be, let's say, 70%, 15%, 15%, or 80-20 split or something like that. Who had a question, Kasina?
Yes, sir. So, sir, can we say of our data that after we do the training part, if it's still not satisfied with our model, then we're using the validation data to change the hyperparameters. Can we put it that way?
Can you repeat? If you are not satisfied, then basically, what do
I
you mean
mean
by
to
not
say,
satisfied?
if we have, for suppose, let us consider the in linear regression we have alpha. I don't remember the name of.
Yeah.
So I mean to say,
See,
after
if your training error or training loss is not going down, then
yeah,
it's a matter of underfitting. That means you have to get a more complex model, or you have to get more data, or both.
or it could be the learning rate is too slow. That is
Yeah. So
also
I'm assuming that your learning has converged.
okay. Fine.
So you're jumping ahead to learning rates. I'm just talking about the high level concepts right now. Okay. So here's a picture that tells you the difference between underfitting and overfitting. Okay. So let's say we are coming back to the same loss where you are taking y minus t the whole squared. Okay. So this is your error or the loss on the training data. And then we have a regularization penalty, which is lambda. Earlier it was alpha, but lambda by 2, or mod of w squared. So you have weights w1, w2, w3, w4. So and w0. So you w0 you usually neglect. So w1 square plus w2 square plus w3 square plus w4 square. Okay, so that is what is you have here. And this lambda is something that you have chosen. Okay. So for different values of lambda, you will get different complex models. So your model complexity will change with lambda. So you optimize, you find its derivative, you for each value of w. So what is y? Y has w built into it. Y has that linear regression w's built into it. So you optimize for the values of w, and you get the least possible error that you can get. And that prediction error would keep going down if your lambda keeps going down. So when I say model complexity is increasing, that means lambda is going down, not up. So this is 1 by lambda. Model complexity is 1 by lambda. So your prediction error will keep going down. Okay, as your model keeps becomes less regularized, and it becomes uh, with lower lambdas. Okay. So the less regularized model will fit very well on the training data. Yeah, error will go down. But your held out data, validation data, on that, the performance, there will usually be a gap. It will actually perform worse than training data, which is obvious because that's not what the training algorithm has seen. It will keep going down, but it will reach a minimum and then it will start going up. So here we are overfitting. We are having too much zigzag in the model. Here it is too smooth in the underfitting case, too smooth that it cannot capture the data complexity. In the middle, it has the capture the right spirit of data complexity, neglecting the noise, random noise in the model, and that is where the optimal is. Okay, so this is a very key concept. This is all what machine learning is about. The difference between underfitting and overfitting. Okay, so usually when you train, You first train a model that can overfit, then you can regularize a bit. Okay, but you, as long as it is not too complex of a model to begin with. Any questions on this? This is a very key concept. Ram Mohan.
Sir, is lambda a parameter of model complexity? Because I was thinking of lambda as a
Lambda is a hyperparameter. Please. Lambda is a hyperparameter. W is the parameter. Okay. Lambda is what is on the y-axis. 1 by lambda is what is on the x-axis here. Okay. And yn minus tn whole squared is what is on the x-axis, not yn minus tn whole squared plus lambda w squared. Just yn minus tn whole squared is what is on the y-axis here in this graph. Okay. Harsh.
So this optimal point, what does it represent?
This represents the best value of lambda.
Okay.
Or 1 by lambda, sorry. Model complexity is 1 by lambda here. Okay, so if it need not be a continuous thing, right? So if you are fitting a polynomial, then your model complexity will be discrete. It will be the degree of the polynomial. Okay, so degree of the polynomial, the best degree that explains the data is the one that will give you the lowest validation error, not the training error. Training error will keep going down as you keep increasing the degree of the polynomial. Any other questions? Take a moment to think about this. This is very important. Ram Mohan.
So this is basically like we are selecting a lambda and then we find the best model that works for it. And then we are plotting the prediction error of that best model.
Yes. So the best model is formed by the optimization process that tunes W.
For a given lambda.
For a given lambda, yes. Sumit.
Yeah, so taking the example of neural network where the number of layers is a hyperparameter lambda.
Right.
So how do you represent that lambda here, map that lambda here?
So not everything can, yeah. So not everything can be represented as neatly as this graph, but this is a conceptual graph. So let's say you keep number of hidden layers to be fixed, just one hidden layer, but you keep increasing the number of neurons. Then the number of neurons will be model complexity.
Okay. So, but if so, in that case, if the number of layers or the number of neurons increases,
yes,
model complexity increases.
Yes.
So why we are calling it 1 by lambda?
No, that is for this equation. No, here it is 1 by lambda. It's not for those models. For those models, model complexity means number of neurons. Here, model complexity means 1 by lambda. For this particular equation, for ridge regularized L2 regularized linear regression, model complexity means 1 by lambda. Okay. Manan.
Sir, in short, can we say first we select a model, we train it, and if it's not working, then we change our model?
Yes. So what changing our model, what does it not working mean? So right. So these are fuzzy terms. So let's define it. What not working means is that your training error is large. If your training error is large, your validation error will also be large. So it doesn't matter. So it means the model is not working. Okay. Then not working means training error could be small, but validation error is large. That is also not working. So either underfitting or overfitting, both are not working.
Okay, sir.
Okay. So if you are in underfitting range, then you make your models more complex to go towards the right of this graph.
Yes, sir.
Okay. If your model is overfitting, it's giving very good training error. It is remembering every training sample you gave to it by rote, but it is not forming the intelligence to perform on the unseen samples. Then you are in the overfitting regime. Then you have to scale it back a bit so that it doesn't become overfitting, it becomes optimal. Okay. All right. Manan?
Sir.
Okay. Nilesh?
Yes, sir. So my question is on model complexity. So
Yes.
I have read that increasing the model complexity means trying to train or learn something very specific to data set or adding more bias. and then somehow it's related to parameters that are increasing parameters like the neuron or something. So can you?
No. Please don't ever call them parameters. Number of neurons is hyperparameters.
Yeah, hyperparameters, right?
Right.
So what is the relation? What is this? That how do we like train for a particular data set? Or what is model complexity?
So model complexity means the model has too much freedom. It can model any training data you throw at it.
Yeah.
So let's go back to this slide. If you look at the graph on the right hand side, overfitted, it is touching almost every black point. Okay, so for the given black points, which are your training data, it is doing a very good job. But if you, in the future, you have a new point for which you only know the X, which is the input, but you don't know the target value, which is the Y, then will that curve, the curve in the rightmost graph, will it come close to that point or not? Okay, most likely it will not come close. Most likely the one in the middle will come closer on an average. Is that clear?
Yes, but in real life, like let's say example of regression or linear regression, what we are changing in it, that it is more making model more complex. Let's say
Yes.
particular.
So I'll give you an example. So linear regression is actually not a very good example, but let's take it anyway. So where is the linear regression?
Examples are what?
Yeah, so here it is linear regression. Let's take the example of here, the single linear regression, right? So here the only thing that you will have regularization on will be A.
Right.
In AX plus B, you will only regularize on A, square root of A, which is that W. So what you are saying is that I'm going to restrict the slope of this line going too far positive or too far negative.
Okay.
Okay. So that means that, let's say there was one of the points, one of the blue dots that was an outlier. It was a house made of gold whose value cannot be assessed based on the number of rooms.
Right.
So it is too far up. Now that particular one should not pull the line too far up, should not increase A too far up. Okay. So for that, to restrict that, I will put a penalty on A square. Okay. Similarly, if I have x1, x2, x3, x4, many x's, then I will have a penalty on A1 square plus A2 square plus A3 square plus A4 square. Okay. All right. Jamian?
Yeah, sir. So how do we choose the lambda?
You choose the lambda based on this graph. You keep checking the performance. You choose lambda 1. You look at the.
No, but how do we start with lambda value? Because there is a R. Lambda could be on R, and first instance will be what will be the first value of lambda to start with.
Usually there is something called grid search. So you take it in logarithmic scale. Okay. So you choose lambda 0.001, 0.1, 0.01, 0.1, 1, 10, 100, like that. And then based on that, you get some estimate of where the lambda should be.
Okay. So, and the second question is in the previous slide where overfitting, underfitting, and the normal one. So overfitting is the more complex model, we can say.
Overfitting is the more complex model, yes.
Okay, yeah, fine.
Underfitting is too little complexity. The model needs to be more complex.
Yes, fine. Thanks.
Sir, can you explain the student in terms of lambda being 0 and infinite?
Can I explain what?
Can I explain this using what it means for lambda equal to 0?
Yeah, go ahead.
And what it means for lambda equal to infinite in terms of graph and equation.
Right. So if you put lambda equal to 0, that means you are not putting any penalty on W square. That is the right extreme of this graph. Okay. If you use lambda is equal to infinity, that means you are trying to restrict W so much that your error between Y and T does not matter at all. Okay. So that is the left extreme of this graph, where mod 1 by lambda is 0. Okay. All right. Ram Mohan?
Sir, is there a reason why we are assigning a 1 by lambda as the model complexity? Like, does this come after derivation or something?
No. Look at the equation, right? If my lambda is 0, then there is no, then the model can do whatever it wants to reduce difference between y and t.
So just because it's kind of like e to the power minus x curve, that's why we are.
No. There's no e in nothing. No, that's just a conceptual curve. The blue curve and the orange curve are just conceptual curves. Don't worry about those. Don't worry about the shape of those. It's just that if you look at this loss function here, lambda is there no entity at all. So left side, sorry, right side where it is less regularized.
Sir, also, is there a significance of the division of 2 in the loss function? Like I understood the square, but division of 2, does it hold a significance?
Yes, because when you take the derivative, your squares will come down as 2. So 2 and 1 by 2 will cut. So it's a mathematical convenience. Okay. Harsh?
So is there a relation between the validation error and the training error? Can the validation error be less than the training error or no?
It can be, but that's usually by fluke.
Yeah, exactly. But then it will mean that because your input is your training error, right?
Right. Your training error is what is here, yn minus tn whole squared sum of that.
Mhm.
That is your training error.
Okay.
Yeah. Okay. So this equation does not have validation error. You compute the validation error separately after you are done optimizing, finding the best use of the. Okay. Sumit?
Yes, sir. So again, talking about lambda. So if we put lambda 0, that
Yeah.
means the yn minus t square, that is mean square error.
Yes.
That is the most significant part.
Yes.
So why shouldn't we let it be like that? Like we have to
Because
minimize the
yeah,
error.
because yn minus tn, just optimizing on that means you are optimizing only for the training data. That means you will keep going down on the blue curve. But that means you may not perform as well on the validation of the test data, which means you will go up on the right hand side on the validation on the orange curve.
Okay.
This is to make the model more generalizable, so that there are test points which you have never seen, which you do not take into account. So you add some flexibility by using that regularizer.
So does that mean that during validation we change lambda as well? No.
No, so you do validation for one lambda. Then if you're not satisfied, you use another lambda. So usually you do for a bunch of lambdas and choose the lambda that gives you the lowest validation.
Okay. Okay. Because lambda is hyperparameter, right?
Yes. Yes.
Yeah. Thank
you. Yeah. Your parameter training is changing W using an optimization process. Okay. Abhinandan?
Sir, I have one question. For a different model complexity that is 1 by lambda, this orange curve that is parabola that we're seeing, is this the curve of the loss function, or is this function of 1 by 2 summation of y1 yn minus?
No. This is not coming from any equation. This is empirical. Okay. Let me make it clear, because this is an important concept. Okay. So how you would do that is, let's say you will say that I will draw a curve. Okay. I will draw model complexity, which is basically, let's say 1 by lambda, or let's say it is number of neurons in a neural network, or it is the degree. Okay. It's the degree of the polynomial, whatever that is. That is your model complexity. Okay, so this model complexity increases, this is decreasing. So you use some value for lambda, some value for number of neurons, or some value for degree of the polynomial. Okay. So you choose that, and then you train your algorithm, and you get some training error. Okay. So this is your error or the loss. It's not just error, it's square of the error. It's basically loss. Okay. So this is your training loss. Then you say, oh, this looks too high. Let me try. You actually try a bunch of lambdas, lambda 1, lambda 2, lambda 3, lambda 4, or 1 by lambda 1, etc. So you get some curve. Okay. And then for each of these curves, you also test on a held out data. Okay. So let me get the right color. So you also have held out data, which is validation data. So usually its loss will be slightly higher. you see that it is higher, but it also keeps going down. But suddenly you see that it starts to flatten out. Usually it will not be like this. It will actually be like a little bit like a zigzag sometimes. And you see that it like either flattens or it starts to go up. Okay. So it's not a smooth curve. It doesn't have an equation. It's empirical, just these crosses. Out of these, you find that this looks like the best pair that I should work with. This tells me that on unseen data, I will get this much loss or this much error. Okay. On the training data, I will get lower error. If I decrease or increase the model complexity, I will get even lower training error, but I will not get as good of a error on generalization error on unseen data. Okay, so it's empirical. It's not like, it's not a curve. It's not, I mean, it's not an equation. The curve is just for representation purpose. It's empirical discrete points. Is that clear?
Okay, sir. One more thing, like in the y-axis that you have written loss. So basically, in the all the validation data also and the testing on the training data also, the loss is basically the yn minus the target function, right?
Yes, yn minus tn. In this particular case, it's yn minus tn squared, sum over n. Okay, let's say divide by n, because your n will be different for training and validation. So you want to normalize it.
Sure. Thank you.
By 2n or whatever, right? So you do this for training points for the blue points, and you compute this for the validation points for the red points. Okay. Sort of.
Yeah, sir. Is there any possibility of the model performing bad in test data after the hyperparameterization of data?
Yes, yes. You could get really unlucky, and your test data could look very different from validation. You could,
so in this case, there could be a possibility of underfitting and overfitting as well.
Could be.
So in that case, could we say that the model is not good generalizable in this set of algorithms?
Yeah, sometimes, I mean, the modeling problem is so complex that it will never give you good test results.
Okay, okay. So in that case, what we do?
I mean, there's only so much you can do. I mean, you can get more training data and increase the complexity of the model. So you cannot increase the model complexity without getting more training data, usually.
Okay, okay.
Ram Mohan?
So let's say we have 3 different models: linear model, squared model, and cubic model for doing some task. So we know which one is more complex by just seeing their degree. So do we assign the values of lambda for each model, or can we calculate it? How is the lambda value defined?
No. So lambda was for a linear model. For a nonlinear model, the degree itself is the complexity. You could add lambda there also. You could have a separate term, double regularization there. Like one regularization can be not double regularization, but you can look at model complexity 2 ways. You can say that I will also look at the power of the, the degree of the polynomial, but I will also restrict the coefficient of the polynomial using an L2 norm of the coefficient. So, but that's a more complex thing. So here, first of all, just think in terms of, if you just have a linear model, then or you have a fixed degree, then you change lambdas, or you have or you change the degrees and look at complexity as a degree of the polynomial.
So when we have a fixed degree, let's say linear model, what does more complex mean in that sense?
So more complex in that case means that your slope can go up or very far down. Slope can become highly positive or highly negative. That's all it means.
Okay, sir.
Right. All right. There's a lot of chat. Can someone summarize if there are any significant questions in the chat? Okay, looks like there are none. So we'll keep moving. Sujay?
Sir, if a slope can become very high or very low, are you talking about that gradient explosion?
No.
Thing?
No.
Oh.
Yeah. You guys are already, you have read so much that you are jumping ahead. Okay. I'm talking about very basic things. No gradient, no nothing. Okay. So when you have data that is, Rishabh, do you want to teach some part of it, or shall I continue?
You can continue, sir.
Okay. So cross validation is basically, so let's say you don't have a whole lot of data, right? So you can't afford to keep some part of validation data out, or you want to get a sense for whether your validation split was generally lucky or unlucky, right? You don't know that. So then what you can do is you can do something called cross validation. So let's say I want to do 5-fold cross validation. So I will split the data into 5 folds. So let's say I have 1000 points. There will be 200 points in each fold. Fold 1, fold 2, fold 3, fold 4, fold 5. Then what I will do is I will use the other four folds to train and test or validate on the left out fold. So I will take 2, 3, 4, and 5 and test on fold 1. Then I will take 1, 3, 4, and 5 and test on fold 2 and so forth. So that way I do it for all 5 folds. And what that tells me is that maybe I got generally lucky or unlucky with one of the folds, but now I have a complete view of all 4 folds or 5 folds. And based on that, I can see what hyperparameter works best for all 5 folds taken together. And then I can use that for training on the entire data. So it's computationally more expensive, but it's a more rigorous technique than just doing a single validation. So this whole complexity versus reducing the error, right? So having too much complexity, but not having good generalization, that is captured in a term that you will hear, which is called bias-variance trade-off. So there's a trade-off between the bias of a model and the variance of a model. So underfitting, for example, intuitively speaking, has high, that means you have high bias. The model it's not the bias the way we think about human bias, that I have a bias that I haven't seen people of a particular country or a particular religion and I think they are like this. That's not the bias that we're talking about. We're talking about bias means that there is some error in the prediction, high error in the prediction. So underfitted models usually have high bias and low variance. What variance means is that if I change one training point, the model will not change very much, so it has low variance. On the other hand, overfitted models usually have low bias and high variance. So coming back to that, this particular one. So you can see that if I change one training point here, this curve can change very drastically because it is very complex. So it has low bias because it is coming close to every point, but it has high variance. Whereas the other two models have, this one, for example, has high bias but low variance, and this one has, let's say, a balance of the two. Okay. Then another key concept to get is the difference between loss and a performance metric. Loss is a proxy for the performance metric. So let's say I am training a classifier to classify between COVID and non-COVID patients, looking at the chest X-ray. So I have binary, so I can look at accuracy of prediction, right? So I want high accuracy or high sensitivity and specificity, but I cannot use that for optimization. For optimization, I need some smooth function. So your loss is related to your performance metric, but you measure performance metric, whereas your optimization performance will actually try to reduce the loss. Optimization process will try to reduce the loss function. So your loss is a convenient expression used for guiding the learning. It is related to performance metric, but it is not the same. Loss may also include regularization, such as sum of the weights squared. Okay. And performance is what you use to judge the model. You don't care about the weights, the sum of square of the weights. You actually care about the accuracy of the model. Okay. So performance on only the held out validation or test data makes sense. Right? So let's look at some questions. Who has raised their hand? Saurabh. Saurabh?
I'm sorry, I didn't lower my hand.
No problem. Sumit?
Yeah, so the last topic, loss and performance. So I would be looking at, as a third person, I'll be looking at the performance, like for accuracy of that COVID kit.
What you report to your manager is performance, but what you monitor on your screen with cups of coffee is loss.
But the target is to improve the performance, right?
Yes, but you cannot improve it directly. It's not mathematically, it may not be mathematically or computationally convenient to improve the performance by adjusting the weights.
Okay. So does that mean that always reducing the loss improves performance?
You try to find losses that will do that. You try to formulate your loss function that will do that. But may not always be possible. There may be some slight discrepancy between loss and performance.
So can you give one example where we accept low performance and low loss vis-a-vis high loss and very good performance, something like?
No, in general, they are supposed to go in the same direction.
Okay.
But I'm talking about individual examples. So let's say there are two examples, both have very comparable losses. One has in fact less loss than the other. That may not be a good example. But let's say they are very close in losses, but their performance, their actual classification may be different. Something like that.
Oh, okay.
Yeah. Okay. Any questions on the chat? Nilesh?
So just a question is there any recommendation how we choose loss function, let's say in certain cases, and how to choose metric?
Yes, we'll talk about it when we come to individual models.
Okay. Okay.
Let's look at the chats quickly. Just go through there. What is split? What is split? What is fold? So you have 1,000 data points. Okay, for 1,000 data points, you have 4 inputs. Okay, sepal length, sepal width, petal length, petal width, and you have 1,000 different species for them, species labels for them. These 1,000 points can be divided into 5 folds of 200 each. Okay, so 200 flowers in one fold, 200 flowers in another fold, another 200 flowers in the third fold, and so forth. So that is a split of the data. Okay. And so you if you divide them into 5 different folds and then you do training and validation on each of the 5 folds, that is cross validation. If you do it only once, then it is regular validation. Let's see, any other questions? One can interpret loss as a negative form of accuracy. Yes, that's correct. So when loss decreases, the accuracy increases. That's correct. Okay, let's come back here. Teeth?
Yes, sir. Sir, if loss is very less, then can it be interpreted as it is overfitted? It can be overfitted.
It can be. You cannot comment on it unless you also look at validation loss.
Okay.
Never interpret overfitting by just looking at training loss. Never interpret so you or optimal fit by just looking at training loss. You have to look at both.
Okay, thank you, sir.
Manan?
So what do you mean by fold?
Fold means a split. So let's say you have 1,000 data points, you split it into randomly into groups of 200 each. So you have 5 folds.
Okay.
Any questions from YouTube? Saurabh, are there any questions? Okay, let's move. So now let's look at performance measurement, right? So performance measurement depends on what are you looking at. If you have a regression problem, then you can look at things like mean square error, mean absolute error, mean, or you can normalize that error also. So map E. So what that means is mean square error means you will just look at y minus t the whole square divided by n. Absolute error will take the absolute differences and divide by n. But then what happens is that it also depends on how your y is scaled, right? So you want to normalize for that also. Then you will look at MAPI, where you will take y minus t divided by y, and then you will take the absolute value of that. Okay, so that's a better metric, so that it's irrespective of the scale of y. Okay, so that's mean percentage error. So you can look at these in your own time. I will skip. So then there are classification metrics. These are all, before this were all regression metrics. So now let's look at classification metric. People think that accuracy is a good metric. right? But it may not always make sense. So let's say I'm looking at cancer patients. I am looking at uh, breast mammography, and I want to find whether this woman has breast cancer or not, right? And 99% chance that she doesn't have breast cancer, 1% chance that she has breast cancer. So if I have a, a dumb classifier that says no one has breast cancer, then I already have 99% accuracy, but that's not good, right? Same with spam filtering, only 1% of emails are spam. So if your spam classifier says there's no spam, so it is already 99% accurate. So you have to look at better methods. Okay. So your chance accuracy is already 99%, but you have to look at better metrics such as precision, recall, or area under curve of a receiver operating characteristic. Let's look at what these are. So these are, so first of all, you have to divide all your test cases or validation cases into a confusion matrix. What is a confusion matrix? It's a 2 by 2 matrix or an n by n matrix where you have n different classes. So let's say you have two different classes, real and spam. So on your in your rows you have actual spam and actual real, and in your columns you have predicted spam and predicted real. You want high true positives. So true positive is it's actually spam and you called it spam, and you want high number of true negatives where it was not a spam and you called it not a spam. You want low number of false positives and low number of false negatives. Okay. These are also called type 1 and type 2 error. So look it up. It's like our standard definition. So accuracy is straightforward. It is true positive plus true negative divided by all the types of samples. True positive, true negative, false positive, false negative. Okay. But that's not always a good measure. So you, like we just saw, so you have to look at two different measures together. Both have to be high. One is precision, the other is recall. Similarly, there is like sensitivity and specificity. So precision is true positive by true positive plus false positive, and recall is true positive by true positive plus false negative. Another way to look at it is something called ROC curve. So ROC curve, what it does is, so let me before that, let me go back to where this curve comes from. There's a concept of a threshold in classifiers. Okay, so what that threshold means is, let's say my output is a binary variable, either 0 or 1, right? So 0 means no cancer or no spam, and 1 means spam. So 0 or 1. So usually my classifiers will not give me a binary 0 or 1 output. One layer below the top, let's say decision, it will give me a probability of spam, PR spam. Okay, so that will be a number that is between 0 and 1. Okay, so let's say it is 0.99. So then it is very close to 1 and I want to call it spam. But now whether, so when should I call it spam? Should I draw the line at 0.5? Should I draw the line at 0.7? Should I draw the line at 0.3? Okay, so by changing this threshold from 0.3 to 0.5 to 0.9, I can get different precisions and different recalls, different sensitivities, different specificities. I can trade off one for the other. Okay, so if I take all 0 to 1, all thresholds, then I can get a curve. Okay, the curve that I will get of false positive rate and true positive rate, that is called ROC, receiver operating characteristic. A very bad curve is a flat, like a straight line diagonal curve, where it is always giving me like a random guess, whereas better ones are towards above that, and the best ones go straight up and then straight right. Okay, the best curve would be if this green curve would go straight up and then straight right. So the area under the curve is what is important to me, because that captures the behavior at all thresholds put together. Okay, so that area should be as close to 1 as possible. If the curve is along the diagonal line, the area would be very bad, which is 0.5. So Jay, what's your question?
Sir, so let's say that if a probability like it determines 1 as more than 0.5 and 0 as less than 0.5. And if the predicted is 0.5, then which class will it belong to? Either 0 or 1.
So that you can define a rule whether it is you take the equal to as on one class or the other class. That's not a usually you never get the exact 0.5.
Let's say if you get by a fluke.
So you have to write something in the program, right? So in the program, do you use less than or do you use less than equal to? It will depend on that.
Okay.
Tirth?
Sir, can you explain the ROC curve?
Yes. So one threshold, let's say I choose 0.5, that would be one
Okay.
point on this curve. It will give you one true positive rate, one false positive. If I change the threshold, I will go to another point on the curve. Give me another. So it will. So let's say I choose another point. It will give me higher true positive rate, okay, but also higher false positive rate. Okay. Ideally, I want high true positive rate and no false positive rate, zero false positive.
Okay.
So with different thresholds, I get different points on this curve, and the area under the curve tells me a summarized behavior of all the points put together, all thresholds put together. Okay.
So what does summarized mean?
Summary.
Okay.
Ashish?
Okay.
Sir, which is the best metric out of it to report? I mean, from cases to cases, it depends. Sometimes we would want to precisely do it, like have more precision or maybe less recall. But what is like overall best metric? Accuracy is definitely not. I'm pretty sure
Yeah,
about
so
it.
there is no one overall best metric. It depends on the situation.
AUC, what do you think about AUC? Is it
AUC is actually a very good metric. I like that, but you know, it's also depends on like who's looking at it. So a lot of, for example, medical journals like to look at AUC. But the question is, how are you going to use the model, right? So that is very important, which many engineers lose track of. So are you going to use the model to screen patients who will be sent for a more expensive test? Are you going to use the model to actually drop patients who you will not examine further, right? So question is, if you overcall cancer, for example, is there a, what is the harm in that? Or if you undercall cancer, is that more harmful? Based on that, you want to see whether you want to go with precision more or recall more.
Thank you, sir.
All right, Neeraj.
So, sir, suppose if I am going for any classification algorithm, and so before, if once I have created the algorithm, I mean, on any data, so these are all the things which I have to see to predict that, okay, this model is behaving properly. So like precision, recall, then AUC, ROC curve, then confusion metrics, and all these things. These are
Yes.
right.
Yes.
And just now you told, like, it depends on the cases, right?
Yes.
Either we should go
So
for precision or either we should go for recall.
Your training process is not actually looking at this. It is after you have trained, you will look at this.
Okay.
Your training process is looking at the loss, which is we looked at mean square error, but in classification it will be something else, cross entropy or something.
So when we run the model, like I was trying it. So when we run the model, we just get confusion matrix values. Now, when we get the confusion matrix value, we have to calculate it by ourselves, right? Is it like in the coding only we do it?
Yes. So your confusion matrix is for one threshold. Your AUC is for all thresholds. Yeah.
No, I was asking, like, suppose we do the coding. Through the coding, we get the confusion matrix values. Like we get true positive, true negative, and all. After that, we manually do it, or in the coding only we do it, like, checking for the precision and recall, all those AUC, ROC curve, all this.
I think there are libraries that will do it for you. I mean, if you give them.
Okay.
Yeah. Gaurav. Gaurav.
Yes, sir. So when we are taking the case of a cancer patient where precision is very important, like we need to identify that one person which might have it. So we increase the interval to maybe if it is from 0.5 to maybe to 0.8 or 0.9. So
No,
that
you will
precision
actually decrease it, right? So assuming your 1 is cancer and 0 is no cancer, you will actually decrease your threshold, right? So that you catch.
Okay, so that will move our precision more towards. I mean, so metric would give us more precise data in that sense.
Yes.
Okay.
Manan?
Sir, are we plotting this curve for validation set or for training set?
Not for training set. The training set, it's meaningless to plot it. It can overfit on training set and then you will be very happy. So it is for validation set. Okay. Kasina?
Sir, so by looking at the graph, we would prefer to have a true positive rate higher and a false positive rate lower, correct?
Yes.
So then here it says higher the area under the curve, that's more preferable. But according to that, if I just have a higher TPR and a low FPR, it would definitely be a lower area, right?
Where is it? Let me get that slide.
Here. Here and AU-ROC curve.
Yeah. So this green curve will rise very quickly to high TPR and low FPR, and then it will go flat to the right. So the area will increase. Okay. All right. Nilesh?
So to explain this ROC, you take an example of threshold, and let's say we are talking about logistic regression, and then threshold would be in hyperparameter, right?
No. Yeah, threshold is a hyperparameter. You can say that, but usually for ROC it is not. ROC plots it for all thresholds. So this is what I wanted to show, right? So this is your TPR, okay, and this is your FPR, right? So what is the range of FPR? It can be from 0 to 100% or 1, and this can also be from 0 to 1. So it's in a box, 0 to 1, 0 to 1. So this is a bad curve. This is a better curve. This is a perfect curve. Okay. So the perfect curve has area 1.
So when we say a particular model has this curve, but if you change the hyperparameters, it will be different models.
Yes. So different hyperparameters will give you different curves. This is for one model. This is for one model where you have said that I will not choose a decision threshold. I will just look at all the outputs and their ideal labels. And this is only for binary classification. It doesn't work for other things.
And so what is the difference between precision recall curve and because in some papers I've seen that they represent the results by both.
Yeah. So you can do the same thing. You can draw a precision curve and a recall curve for different thresholds.
Okay.
And you don't have to draw ROC, AUC curve. Neeraj?
Sir, so like suppose if I'm taking the case of logistic regression, so there also in sigmoid curve, we define the threshold point. Like sometimes like 0.5, if more than 0.5, then it is negative, less than 0.5, it is positive. So is it like that threshold point, on this basis only we decide that is this 0.5 or 0.4 or what? And this AUC ROC curve, or how we decide?
No.
In
AUC ROC curves tells you what is the overall performance if you use 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, everything. It tells you the general performance of the model. It doesn't pick a specific.
So the threshold point we take in sigmoid curve, that is different, is it?
That is different, but that will, if you choose a threshold point, let's say 0.5 or even 0.4 or 0.6, then you will get a different precision and recall value. You will get 1 point on this green curve.
Okay.
Ramohan?
Sir, in the best case that you described, the box one, sir, the edge of the box, I understand when the TPR goes to 1 because it's like the true positive rate is like highest.
Yeah.
But when the FPR starts increasing, what does that line represent? Why is the FPR increasing, and how is it the best case?
No, it doesn't really increase. It's just like so usually you think of it as not the theoretical square curve just means that you can operate at the left top point. But you never get a curve like that. There is always like slightly less than that, right? So that means you can still misclassify a couple of points, and that's why you have the top portion would be like slightly slanted. It won't be flat. We are taking too much time. I would encourage you to look at ROC curves and so forth. We should wrap up the lecture. Okay. So let's quickly finish this. I will skip this gradient optimization. This we will talk about it later. Basically, it tells you what is the optimization process. So if you look at the weight space W, so for a bad weight, for a wrong weight, your cost will be high. But then for a correct weight, the cost will be low, the loss will be low. And then if you go to the other extreme, again the loss will be high. So the optimization process finds this point, and the characteristic of this point is that its slope with respect to W, the gradient with respect to W is 0. So basically we use something called gradient descent to change the weight, but not just one weight. It will be many weights or many different coefficients to find the lowest point, the lowest cost for a given set of hyperparameters. Okay. Skipping. So unsupervised learning, we already talked about it. I will skip that. Uh, One thing that I will talk about is that your weights, because W1 is multiplying with X1, W2 is multiplying with X2, and so forth, is intimately tied to the range of X1, X2, X3, the input features. So it is very important that you don't use two features, two inputs. Let's say number of bedrooms and square footage of a house are two different features and two different units. It's very important that you don't throw them just as it is in the model. You normalize them so that they are in the same range, so that one of the weights is not too much influenced because of its input. Okay, trying to reduce the error for that input with respect to that input. So you can do two standard types of normalization. One is standardization. You make every feature zero, mean, and variance one, or you use a min max scaling, or you use something like a 1 percentile, 99th percentile scaling, so that the ranges are between 0 and 1. I think you have already looked at it in data science. Okay. So that's pretty much it. Now I will hand it over to I'll hand it over to Rishabh. Let me go here.
Yes, sir. So should we continue that notebook part today?
Yeah, let's finish it. Let me make you co-host.
Okay, fine.
Okay, I will drop off for a bit. You guys, you continue.
Okay, so hello everyone. I will walk you through the notebook which we have prepared, and it has already been shared. So yeah, am I audible?
Yes.
Yeah, yeah.
Okay, yeah, thank you. So just the basic libraries, we are loading it. We have covered this, I think, a lot of times, and here are these some of the classifiers. So as you can see that in case of means in scikit-learn, we have lot of packages or libraries, classifiers, all these things. So it's better to have a look at sklearn tools for machine learning. Like you can see that sklearn.ensemble, we will cover this in detail in the second lecture. So we have imported couple of classifiers like regression, random forest, all these things. Though all these have not been used in this notebook, we have just imported it once. Then this trend test split, grid search, accuracy score, mean absolute error, these things. So these things are available in the in sklearn. So you can simply go through all of them. You can read about it just to have an idea like which library does what. Okay, so here we are just as sir has mentioned in the slide, that overfitting means the error on train data is means on train data the error is very low, but when testing the same model on test data, the error goes high. So that is the case of overfitting. So we are loading one candy data over here. So okay, let me load this also. So yeah, so we are loading one candy data. So basically this is a data set which are having means like, let me show you. So as you can see that we are having some of the brands of chocolates, and whether there is chocolate content, fruity, caramel, and we have to predict this level like win percent. So what are the chances of one particular chocolate being popular? So this thing has to be predicted like a win percent. So this becomes a case of regression. And then so we are just so in this case you can see that this is the label which we have to predict, and apart from this the remaining all these features can be called as features. So these are features and this is the label. So here we are extracting the features and label from the data set. So yeah, so y becomes our label, that is win percent. And in case of x you can see that this name does not add much to the data set, to the value of the data set. So we are dropping the name of the this competitor name and the level obviously. So now we have extracted our x and y from this data set. Okay, and now moving forward, so we are just splitting this x and y to start using our model. So as you can see that we have used train test split. Okay, and then the x, then y, test side. Test side, it means that point 2 means use 20% of the data for testing. Here we are not using the validation part, we will do it later. So here we are having one train data and one test set. Okay, by preparing our model on train, we will evaluate its performance on test set. That is the simple. And the random state, it is basically used to reproduce the results, because every time you run the this code or this line, it will shuffle the data and then it will split it. So that's why if you want to reproduce your results, so you will put one random state. This value can be anything, 1 2 3 1 4 5, it can be anything. Just this argument has to be passed with some fixed number. Okay, now we are instantiating one classifier, sorry, it is regressor actually, random first regressor. And these are some of the parameters which we are specifying. Okay, you can also denote it like simple random first regressor, and we cannot pass any of these things. Means you can have simply like this you can also do. Let me delete these things. You can also have just this will also work, but here we are specifying all these things. Okay, then we are fitting this regressor on our train set. So RFR, the name of the regressor, and then fit X train, Y train. Okay, and then we are calculating the error of this model on train data and test data. So let me run. I hope this cell is available. Okay, and it is taking a while. Uh,
Meanwhile, we can take questions, Sudhakar.
yeah, sure. We are having
Sumit,
questions. Okay.
Sumit, you can ask.
Yeah. So my question is, those features, those columns which you are taking to calculate the win percent. So there must be some weights assigned to those columns, right?
Okay, so we are not, see, this task is done automatically by our regression. So whatever model we are assigning, this model will fit accordingly. We are not specify any weight as of now.
But the model will assign some weight, means using these columns to calculate the win percentage. So obviously there will be some weightage used, right? Either
Yeah,
model will
so
use.
that is must, so that is must, like model will assign accordingly weight. Suppose you are having like you are having 1 2 4, means like you are having x 1 2 3 and corresponding output is 1 4 9. So now the model will have to decide which shape or which function to use so as to map 1 to 1, 2 to 4, and 3 to 9. So that is the job of the model. Means we are not programming it explicitly.
Okay, okay.
Yeah, so yeah, now I will run this particular cell. So yeah, so you can see that we are having training error is 8.99 and the testing error is 8.57. There is a significant difference, though it's not high, but it's high, like it's 4 and it's more or less 9. So the training error is very low and testing very high. So that's why we can say that model is doing on training data, but it's not doing well on the test data, which it has not seen before. So that's why this is a case of overfitting. Yeah. So now, now we will move towards parameter tuning, like okay, hyperparameter tuning. So it's
Sudhakar,
like
people have some more questions. Sorry, people have some questions.
Sure.
Manan.
Yeah.
Can you explain? Can you brief about the arguments of a regressor?
Yes, definitely. You can print it out. Like suppose I want to see the anyway it will show I think here also. Okay, so we can simply print out here like rfr dot get params. I think these arguments. So my internet is a bit slow, so yeah. So by looking at the documentation as well, or you can passing, okay, so you can see that there are these arguments are there like criterion, maximum depth, maximum features, maximum leaf loads, maximum samples. So you need to read about all of these things, what each argument does, and accordingly you can assign value to them depending on your model or the need of your model. So these are some of the arguments used in this particular regression.
For example, number of estimator is the number of trees that we are using in this regression model, and maximum depth is the what should be the depth of the tree for each tree of that model. So likewise, there are a lot of different parameters, and like here we have not mentioned all of them, so they are taking their default value. So this is what we will do in the grid search to tune these all hyperparameters. Not all of them, but we can try some of them.
Yeah. Any other questions we have?
People are asking why is hair overfitting?
Why is okay? So means you can see that on train data, like after fitting the model, we are using the same model to predict the values of X train. Okay, and then we are calculating the error also, like Y train means these are the standard like mean absolute error. So it will simply means subtract Y train minus this prediction. So the value of this error is 3.99, while the value of this error on test data is 8.57. So means you can see that this model is not doing well on the data which it has not seen before. So that's why we can conclude that it might be overfitting on the trained data. So we need to regularize it, or we can also tune it further to get better results.
Okay. Pratigya, ask.
Yeah, so I want to ask that all these parameters which are given here, after you have typed this command, get underscore parent, are these all the parameters which are x1, x2, x3 in the equation of linear regression?
No, these are hyperparameters of models.
Okay. So what
So
are
your final model would look like okay. Yeah, please go ahead.
So in the equation, linear regression equation, y is equal to a x1 plus a1 a2 x2. So what are x1 x2 x3 here?
So x1 x2 are these things like chocolate, fruity, caramel. These things are x1 x2, and now the weight which this regressor is assigning, that will be the w1 a2. These are simply x1 x2, these things, and this is the y.
Which one is the y?
The last one, the win percent. You win.
Okay.
So we have to predict.
Okay. Okay. And okay, so all those which have been represented by a parameter are all hyperparameters which are shown downwards on the screen.
Yeah.
Okay, fine. Yeah, thank you.
Sumit.
Yeah, I have this similar question. Can we see the model which we have developed using this library?
So this is
There are
a
something like
yeah. So,
yeah. I think there is something COEF. I don't remember the exact line, but I think this is COEF, which might give the weights which it has.
Sudhakar, run on new cell. It will take whole time.
Rishabh?
Yeah, I am connected.
Okay, sure. Yeah, there is some.
Hello, am I audible? And is it visible to everyone? Okay, fine. So, where- yeah, so we were looking at this random forest regressor model. So we have trained it, and this we can get all the details of the hyperparameter using this model dot get param function. And coefficient, so basically random forest regression is a tree based model. So basically what it does is it creates here, since n estimator is 25, so it creates 25 trees and it will assign weights to everyone, and then it will calculate a weighted summation of to calculate this output win percentage. So there is not any regression, like there is not any equation such as we looked at regression part. So we will be covering random forest in more detail when we look into the tree decision part. Here we are just focusing on how to implement the model. Okay, so now we will look upon the a bit about upon parameter tuning part. So this is a tic-tac-toe data set. If you can see, if you want to see the first 5 row, then it is like these 9 entries are the entry of the matrix of tic-tac-toe, and this class true is like whether it is solvable or not, whether somebody wins or not. So here we are changing the column name class to target, because class is a reserved word in Python. So it might get confused, so it's better to it is not preferable to use reserved words while dealing with data. So it will just now change the column of a target variable as target. Now we will, since we want to feed numerical data in our model, so we are exchanging all the x entry, which are these x, and all the o entry to 0 and x entry to 1. These are just, since this is a binary, binary input, so we can change it to a numerical feature. And just to have a look, what is what are the number of unique values in our target. So we know there are only two, true and false. and you can see this is a kind of imbalance set. So there are different methods to deal with a imbalance set. Some of them are oversampling, undersampling, or some smooth. Here we are not using that. You can have a look on your own. And now we are since the target variable also should be we are just converting them into numerical value. So lambda is a function, so when I'm using lambda, we can write the function in the same line. And so whenever x is equals to false, we are putting the value of x as 0. And if it's true, then we will be replacing it by 1. So on running this, again you will see the same number of unique value. Instead of true, we will get 1, and instead of false, we will get 0. So now we will try to segregate our data, basically to filter out what are the target variable and what are the input variables. So y is our target and tic tac data is x, that is our input variables. And now we will map all those zeros and x to o and x to 0 and 1. So basically it will convert our whole data to a binary form. And if you can see, this will be our input to the model. And what is nan here? So you can see there are b. So b is basically like we have not entered any value for that part. So while mapping, since we have not defined what should be mapped to, so it is just assigning it nan value. And now we are using impute function to replace these nans. So basically impute is using a mean value to replace all nan values. Now let's see, is there any question? Okay, Pratigya. Pratigya, do you have question?
Yeah, Rishabh, regarding the question which someone asked that can we print all the weights which the regressor is assigning?
That random forest regressor.
Yeah, so we can simply pass one argument that is dot feature underscore importances underscore. So yeah, so where we have assigned the RFR, no, maybe below. Yeah, so here, yeah, coef, just delete this coef underscore. Okay, RFR dot feature underscore feature. No, feature RFR dot feature underscore yeah, the same one. The one which is, yeah, just enter it. It should show the weights which, yeah. So this is the array which is showing the weights which has been assigned.
So let me clarify for random forest. Actually, there are no weights. It's showing feature importance. It's showing a summarization of all the decisions in the decision trees of the random forest. It's not. I mean, these are not weights in the sense of like a regression or a neural network.
Okay, so do we have more questions? Okay, so let me continue. Yeah, so here we transformed our here we have imputed the value from and replaced all nan from the mean value of this column for the corresponding columns. Now we will be dividing our, basically splitting our data to train and test set. We are not using validation data here. And we are splitting on 75:25 ratio. now we are defining two lists, test scores and train scores, and we are iteratively applying the model. So this is what we do in a crude manner. We can say this is what we do in grid search. We will look into that later as well, and we will try with some different value of n estimators to see which one is working the best. And we are just appending all the accuracy scores in both the cases. There might be some other metrics which can define this problem better. Here we are using accuracy score, and we are appending them to these two lists, and these are the result that we got after trying with an estimator equals 1 2 4 10 20 50 these values. So while plotting the graph, you will get a better visualization as we are increasing the number of estimators. Our model is getting better and better because both the train and test score is increasing. I mean, train is constant, but test score is increasing. So most of all, we have reached that optimized value here. And so basically, why we are getting score or accuracy score of 1, because tic-tac-toe already have a very well defined algorithm to predict the outcome, so model is able to judge that. And well, it's not a very good problem to solve with machine learning. Here we are just making you familiar with the model. Now we will look into the visualizing effect of feature normalization part. Do we have any questions before that?
Please explain the above code.
Which code?
I think that testing the score which we just plotted.
This one?
Yeah, the above one means where we are appending all the scores in the form of a list.
Okay.
Yeah, this one.
So here, for every estimator, we are fitting the model on Xtrain, and then we are predicting on Xtrain and storing it into a variable named as train predictions. Then we are appending these variables into this is an accuracy score function which we have imported using sklearn library, and we are appending these accuracy score for each estimators in this train scores and test scores list. And after this exiting this for loop, these two commands are running, and they are printing these values in the stored test score and train score lists. So basically 0.94 is the accuracy score for training data set when we use only one estimator. And this is what we have plotted here. And we can see on increasing the number of estimators, our model is getting better and better. So now we will look into the visualization effect of normalizing a feature. So here I am using a toy data set. So this is how our data frame looks like. So if we plot the histogram for two numerical variables, then we get something like this. So we can see that it's H data set. Yeah, so here the salary range is 0 to 75,000, and age range is from something 20 to 80, which have a very different range. Since the range values are very different, so as sir explained, we want to normalize or either normalize or standardize the feature. So we can use these codes to for a normalizing part into on a scale of 0 to 1, we can use min-max scalar. So min-max scalar is a function provided by this pre-processing function, and it is being imported by scaling libraries. And dot fit transform, here we are implementing that function on x. And what is x? X is the column 1 and 2. So basically these two columns, age and salary. So after normalizing it, we get something like this. And in the same way, we can standardize the column as well. So yeah, so that's the two way we can normalize or standardize a column or a feature. Now we will be implementing a XGBoost model. So we will look into the detail of these model when we will cover decision tree session. And here I am using a diabetes data set. So if for looking the of the columns, these are the columns that we have, and diabetes would be our target variable. And diabetes is a binary variable. So basically this is, we want a binary prediction of whether a person have a diabetes or not. +1 means they have a diabetes. So if we want information of whole data frame, then we can get using this command. Okay, so should I need to take some questions?
Yeah, Ayush.
Yeah.
Yeah. So in the previous tree example that you just mentioned, right? The
XGBoost or random forest?
Random forest.
Okay.
The coefficients don't really represent the what you say. The importances are not really the coefficients of the tree.
Right. We covered that.
Right. So my question is, let's say, for example, the model got trained on 10 variables, 10 data points in which sweetness is, let's say, um, uh, if the chocolate is sweet, then let's say it wins. So of the 10 data points, chocolate is sweet. So the sweet got more weightage. So does that means the higher value for sweetness corresponds to higher, the importance corresponds to coefficient? Like I didn't get the point where you mentioned ki it's not same as coefficient. So if the relative,
Yeah, because there are no coefficients in random forest. It's a different kind of a model.
right.
So that's what we mean. So the importance is calculated in a different way. That if I remove this variable, then how much does my accuracy suffer? So that's how it is measured. So we will come to that when we actually talk about random forest. So right now, the model inside is too complicated to actually print and show anything other
Right.
than this summary of variable importance. So I think we should move on. It's gone on too long. So random forest, when we come to it, we'll explain it.
Great.
So do we have more questions, sir?
No.
Okay, so now we are checking whether we have any missing value or not in this diabetes data set. So since all of them are showing 0, so we don't have. And if we want to see the counts of diabetes column, then we can use value count command. Now to show to plot this data, we can use a Seaborn library. So now again, this is same as what we did in one of your assignment. We are plotting histogram for every feature. So these are the data exploratory part that you can do on your own, and you can explore something new as well. Again, I am plotting a correlation matrix in which I have used a mask, and then just plotted the lower triangular for the correlation matrix. So the according to the scale and color, we can see the one which are highly correlated and or not. So here I am using just all the variables in the model and not exactly doing this feature extraction part. So this label is our target value, and feature df is all our inputs for the model. Now again we will split the data in 80:20 ratio. 80 would be for a training data set, and this is xgb. So basically we have imported xgboost as an xgb, and and we are using xgboost classifier model with a learning rate of 0.01. So there might be another other hyperparameter as well. Here I have passed only one, and these are the by default parameters. So we can tune them as well later when we will see the grid search part. So here we have trained on X train and Y train. So now we will use this trained model to predict for training data set as well as test data set. So with a but when we round the accuracy with 2 digit after a decimal, we get 80.62 accuracy percentage. And on test data set, we are getting 77.2 set. So since it is a categorical variable, our target variable, so we can have a confusion matrix for that. So basically 86 is here the 86 is true negative, and 33 is true positive, 10 is false positive, and 25 is false negative. And these are the formulas to calculate these as sir have explained in the slides as well. So we can calculate various metrics, and you can cross check whether it's right or wrong. So these are like classification report is a function that is provided by again scaling, and we don't have to explicitly write all codes. We can just use it directly. Now we can plot an ROC curve for the same problem. Here XGB CLF is the model that we have defined, and predict probability of X test is basically like this model is already a trained model, and predict probability when we are putting X test, then it will, since the target variable have two targets 0 or 1, so it will give the probability of having class 0 or having class 1. So now since we are only interested uh, to find out who are suffering from diabetes, so we are taking the one which which is having a target value of 1, and this is how we can get true positive rate and false positive rate. And ROC curve is a function that again we are importing from scaling.matrix, and then we are just plotting the TPR versus FPR curve. And as sir explained in the lecture slides, so this will be our ROC curve, and this is just like y equals x line, and these are for the label, and this is how we can plot ROC curve. So yeah, I think I'm done with the notebook. Do we have some questions?
One, Naveen Kudari, I think.
Yeah. Can you show one simple example for image data set? Like,
We'll
you
come to
can.
that later. I think right now this is what we have.
Oh, okay. Okay. Yeah.
Naveen, are you done with your question?
Yes, I'm done.
So is this over?
Yeah, sir.
Okay. All right. Okay. So I guess then we are all done. Thanks, everyone.
Thank you, guys.
Thank you.